Question 6 of the practice final reads, given A, which is the vector potential, is equal to B naught K1 S hat plus K2 phi hat minus 2K1 S plus Z Z hat. So I'll write that. We have our vector potential A is some constant with the right units B. K1 also with the right units is some constant S hat plus K2 phi hat minus 2K1 S plus Z in Z hat. So given this vector potential, which right away we can see is in cylindrical coordinates because of the S hat, the phi hat, and the Z hat. So that's going to be important coming forward. And then we have part A says find the magnetic field B. So we recall right away that B is equal to the curl of our vector potential. So our magnetic field is the curl of our vector potential, and in this case in cylindrical coordinates we just have to do the curl and find B from A. So I have written here the curl in cylindrical coordinates. Write that down quickly. So we have some constant B naught, and then we have 1 over S d of AS, or AZ, sorry, over d phi minus d of A phi over ds S hat. And again, this is just the standard curl formula in cylindrical coordinates, which you can get from a formula sheet. I just have it written here. AS by dz minus d of AZ by ds phi hat, and then plus 1 over S. The final term is d by ds of S A phi minus das by d phi Z hat. And we'll put the big bracket around all of that. So this is our curl, and we can do this in terms of the terms. So we have, by plugging in what is AZ is just this component of A here, A phi similarly, so each of the components come from the different terms in the vector. And this is just 1 over S, d by d phi, negative 2K1, S plus Z, minus d by dz of K2. Put a big bracket around here. This is an S hat, and then plus d by dz K1S minus d by ds negative 2K1 S plus Z, and brackets around here. And this is all in the phi hat direction. And then finally we add 1 over S d by ds of S K2 minus d by d phi of K1S, and that's all in the Z hat. So again, just so we can see what's happening here, we have our general formula for the curl of A in cylindrical coordinates, and then all I've done is plug each term, either AS, A phi, or AZ, according from this function here, into our curl. And then we just take the derivatives, which gives us B naught. And then we have a d by d phi, and there's no phi term here, so that's 0. A d by dz, and there's no z term here, also 0, so we have 0 S hat. Plus, and then we have the derivative here with respect to z, there's no z term. With respect to s, so of course we have a negative and a negative, gives us a positive. 2K1, d by ds of s is just 1, so 2K1 phi hat. And then plus our last term, which is 1 over S d by ds of SK2, so we get a K2 term from there, and negative d phi by this term here, which has no phi dependence, so it's just 0, so we end with K2 over S Z hat. So our final magnetic field that we find is B naught times the vector 2K1 phi hat plus K2 over S Z hat. So again, the main thing to recall in this question is that this is the formula we want to use, that the magnetic field comes from the curl of the vector potential, and then is simply the usual crunching numbers and taking derivatives that we have done on the previous practice midterms, where we just find out what the derivative formula is from our formula sheet, plug in all the correct terms depending on the S hat, phi hat, or Z hat dependence, work through the derivatives, and end up with some vector, which is the magnetic field. So now that we have found the magnetic field in part A, part B asks find J for the B. So J is the volume current density from our magnetic field B. So right away we recall that the curl of B, the curl of our magnetic field is equal to mu naught times J. This is one of Maxwell's equations, where again J is the volume current density. We can solve for J, which says that we have 1 over mu naught curl of B. And again, B is in cylindrical coordinates because we have it directly from A. So again, now we just have to take the curl in cylindrical coordinates of our magnetic field. So I'll write this out. J is equal to 1 over mu naught. Again, the curl just comes straight from the formula sheet. 1 over S d by d phi of, it's going to go directly into the components and skip the step of writing out the entire curl formula because we did that in part A. So we have B naught K2 over S. And then you can just check at home to make sure all the terms line up correctly. D by dz of 2K1 B naught. This is in the S hat direction, plus negative d by ds of B naught K2 over S in the phi hat direction, and then plus the z hat term, which is just 1 over S d by ds of 2K1 B naught times S in the z hat direction. So doing these derivatives and working through, we have a B naught in all the terms, so we can factor that out. We get B naught over mu naught, and we have, again, the derivative with respect to phi. Derivative with respect to z of two constants is just 0, so we have no S hat component, plus to take the derivative with respect to S in this term here, which gives us a K2 over S squared phi hat, because the negative will cancel with the negative we obtained from the derivative. And then finally we have plus 2K1 over S of our z hat term, because we take the derivative with respect to S, and then we have a 1 over S factor. So finally we end up with that our current density J is simply B naught over mu naught, and then these terms here, which gives us K2 over S squared phi hat plus 2K1 over S z hat. Just check this here quickly. Yep. Okay, so again, to walk through the steps, first we recall that the curl of our magnetic field B gives us mu naught times the volume current density, which is just a Maxwell's equation. We have that J then is equal to 1 over mu naught times the curl of B, and that's what we want to solve for, is J given the B that we found in part A. We can work through the curl from the formula sheet. The formula is this. I've just subbed in each component to begin with and negated some that are automatically going to be 0, given that there's no S hat term here. You take the derivatives and you end up with the current J is B naught over mu naught K2 over S squared phi hat plus 2K1 over S z hat. So again, this is just, first thing you need to recall is this formula here, and after that is taking derivatives, plugging numbers, and ending up with the correct current density. So the last part of problem 6 is C, and that says for the Coulomb gauge, we want to
just continue in like a couple seconds.
For the last part of question 6, we want to look at C, and it asks us to find whether or not this magnetic vector potential is in the Coulomb gauge. Now we want to recall that the Coulomb gauge is defined as the divergence of the vector potential A is equal to 0. So we want to find what the divergence of this field is, and again from our formula sheet we have the general formula in cylindrical coordinates, d by ds SAS plus 1 over S d a phi by d phi plus daz by dz, and we have our general form of the vector potential, and we want to simply take this divergence, so we have 1 over S d by ds of B naught K1 S squared, because we have an extra S factor in the derivative, plus 1 over S d by d phi of B naught times K2, and finally plus d by d phi, or sorry, d by dz of negative 2 B naught K1 S plus Z, where again each of the AS, A phi, and AZ terms come in collectively from the vector potential given in the question. We take these derivatives and we end up with 2 B naught K1 plus 0. That first one comes from this derivative here. We have d by ds of s squared is just 2s divided by s is 1. Or sorry, 1 times 2. Plus 0 plus the derivative with respect to z gives us negative 2b naught k1. And of course we have 2b naught k1 minus 2b naught k1, which is just equal to 0. So indeed, our vector potential A, the divergence is equal to 0, which means that we are in the Coulomb gauge.